Lesson 2.4 is now going to be dealing with what we call complex numbers. What we're really going to want to understand is this objective down below, is how are we going to deal with when we solve something like this quadratic and there's a negative underneath the radical. So we'll also have to be working with these results that we get, which are these complex numbers, and we'll have to do these operations such as adding, subtracting, multiplying, and dividing. Here's a quick warm-up that I would like you to try. Give it a moment, go ahead and go through these. Don't forget these two properties that we have right here, which if you have the product of two things underneath the radical, we could always break them apart. And then same thing if we have a quotient underneath the radical, you could always individually take the square root of the top and the bottom. So simplify the following, and these would be your answers. The square root of 9 simply would be 3. Here's the thing, leave no perfect square underneath the radical, so I'm going to go ahead and say, hey, I know some perfect squares that are underneath this square root or this radical. I could take 25 times 4, right? And then so there we could break those apart, the square root of 25 times the square root of 4, because hey, these are two perfect square factors of 100. And then when we simplify this, the square root of 25 would just be 5. The square root of 4 would be, well, 2, so this would be 10, 5 times 2. And then you may say, well, why did you do all of that? Because the square root of 100 is just 10, right? But I wanted to remind you of this wonderful property, of course, that yeah, you could just take the square root of the whole thing that's underneath the radical, or you could always break them up into factors. Alright, so then therefore this one I'm going to do the same type of route. Leave no perfect square factor underneath the radical. So here I would kind of go through that list of perfect squares, such as 4, 9, we have 16. I'm going to stop because 9 is a factor of 18, so I'm going to rewrite this as 9 times 2. Haven't changed anything, right? Because 9 times 2 is equal to 18. But now I can use that property that I just did above, and I would get 3 square roots 2. Leave no perfect square factor underneath the radical, and I did not. I pulled it out of there. Alright, now this one, if you try to do any of these on your calculator, you would succeed in getting some sort of decimal number for this one in particular, or these perfect squares. But this one, we would get an error. So what we're going to have to try to figure out is how do we deal with something like this, because this is almost identical to warm-up number 3, except for we have this multiplier of -1 that's involved. So this would be the same thing as what we just had, the 3 square roots 2, but I would also have this -1 square rooted as well. So that's where we come to what happens when you try to square root a negative number. Well, one video that I watched one time said neg on the inside, make it I on the outside. So just like we had that problem, the square root of -18, then I'm going to say, well, the square root of -1 times the square root of 9 times the square root of 2, what we're going to then say is, hey, this is I, 3 square roots 2. The best thing to do is put that right before the radical. More often you would get the real part, the I, and then the square root if you had any square root left over. Right? So also another thing to keep in mind is if you ever squared I, that would be the same thing as squaring the square root of -1, so that would just be -1. We'll be watching out for that when we do multiplication. Complex numbers, this is going to be our new type of number that we're going to be working with. One thing that I would just kind of like to accomplish is that complex numbers are a huge family of numbers that also include real numbers and also include imaginary numbers. Now imaginary numbers are any kind of number with an I piece to it, so that's square root of -1. If you get any kind of square root of a negative, then that's when we have an imaginary number. But if you have a real part added onto it, such as 4 plus 4i, this would be our complex number that falls in this type of form, where you have a real part plus an imaginary part. Alright, so let's do an example of write the complex number in standard form. So here I'm going to have 1 plus, and this is where I'm going to say, hey, I know that I'm going to have an imaginary part. So here is that -1 factor that I can eventually kind of break apart from what's underneath the radical. And then 4 is a factor of 8 that happens to be a perfect square, so I'm going to set that aside. And then we have that 2 left over. So then I'm going to have 1 plus the square root of negative 1 times the square root of 4 times the square root of 2. And here's where my I will fall. Okay, times, and then here's that perfect square that I identified, so 2 times the square root of 2. So the best way to write this would be 1 plus 2I square roots 2. Alright? If you left it like this though, I'd be fine with this. Also, just notation sake wise, you don't hardly see this ever, only because you're not really sure is that I underneath the square root or not. But I mean, if you wrote that technically, just be very clear that that I is not underneath the square root, because that'd be weird. Alright, same thing here. Let's write the complex number in standard form. So here I'm going to try to identify some perfect square factors. And of course, I can already see I'm going to have a negative 1, which will result in an I, and then 25 times 3, right? So 25 is one of those perfect squares, and when I break this apart, by that property of radicals, we can break these factors apart. There's my I, square root of 5 or 25 is 5, and then square root's 3. So I'm going to write this as 5I square root's 3. And this is in standard form. You could put 0 plus and then have that, but we really don't need that. I just know that this is an imaginary number that is in standard form complex number form. So now that we know exactly what a complex number is, we're going to have to deal with these operations, these 4 basic operations. The first one I'm going to address is the adding / subtracting. The best thing to know about this is that you're going to want to combine all like terms, and real numbers cannot be combined with imaginary numbers. That's why we have a real part plus an imaginary part, because they don't combine. Much like 2 plus like x do not combine, neither would 2 plus I. Okay, so don't make this into like 3i or something like that. Okay, so here we'll have to be very careful with subtraction. What I am going to do is here's one complex number and then plus, and I'm going to turn this into negative 1. Okay, I haven't changed anything at all about this. It's still technically 8 minus I minus, and then this whole 4 minus I. But now I know that I have to distribute this to each one because I'm subtracting this whole complex number. So here I would have 8 plus negative I plus, and then this negative 4, and then plus positive 1i, right? Or we could do like we have been doing with the subtraction if you prefer doing something more like this. Hold on. You could always turn this into a plus, but then negate the following signs. Okay, and then I like to turn this into plus and negative. So the idea is the associative property of addition states that if you're just adding a bunch of terms, which we are, you can drop those groupings because the groupings don't matter when you're adding a bunch of things. So here you could have had those parentheses, but I'm not even going to put them because again we're just adding a bunch of terms. It does not matter what order. So I am also now going to use the commutative law of addition that says that hey, I can take negative 1i plus 1i, those actually will cancel each other out, right? When you combine those, we'd get 0i, and then we would have 8 plus negative 4, so 4 plus 0i, which we can just write as 4. Alright, multiplying complex numbers. This is very similar to, I don't want to say treat I like a variable because it's not. I is a very specific number, that square root of negative 1, but we can still kind of treat it like a variable in terms of the operation. So just like if you were to have 4 plus 5x, whole quantity squared, we're going to do that same type of foiling that we would have done with that x being there. And what we're going to do is we're just going to multiply everything in this group times everything in this group. So 4 times 4 is going to be 16 plus, and then I'm going to take that 4 times the 5i, so the real parts will multiply and we'll get 20, and then I will have to leave because they're not in the same group of numbers, so just 20i. And then I'll have to take this times everything, so I'll get plus 20i, and then 5i times 5i. So I have 5i times 5i. We can go ahead and look at the 5's, multiply those, and look at the i's, multiply those. So what we're going to get is 25 and then I squared. Alright, be aware of I squared. That's a red flag. If you ever see I squared, you should always change that into what we know. If I equals that square root of -1, then I squared is equal to the square root of -1 squared, and these cancel each other out. So what I'm going to do is take out that I squared and put in -1 instead. So that's going to multiply. We have 16 plus, I'm going to simplify these. So we have 20 i's plus 20 i's, we would get 40 i's, right? And then 16 plus 40i. Now this is going to change into plus -25. And now if I combined these, because it's addition, order does not matter, I am going to get -9 plus 40i. There is our complex standard form. Of all the operations, the division is a little bit more complex. So division, the main thing about that is we're not really actually dividing these. What we're going to end up doing is getting rid of a complex number on the bottom. We do not want imaginary numbers on the bottom, just like we don't want square roots on the bottom. It's just one of those math etiquettes. It's a little bit confusing to look at, so we change it. So we can multiply top and bottom by the denominator's complex conjugate. That's one way to do this. There are other ways, but this is the main way that we use in order to get rid of that imaginary part on the bottom. So complex conjugates, a pair of complex numbers where the imaginary part is the opposite of the other. So for example, if we had 3 minus 2i, it would be the exact same thing, but you would have a plus 2i instead, the opposite imaginary parts. So in this case, when I'm looking at this, what I'm going to do is I'm going to take and multiply by the top and bottom the conjugate of the bottom. So it's going to be instead 4 plus 5i, and of course I have to do it to the top, because if I choose to multiply the bottom by something, a bottom of a fraction, then you got to do it to the top to keep it equivalent, or keep it equal in value. Okay, so it looks weird, but this is essentially 1. I've multiplied a fraction by 1, haven't changed it at all really. So this top part I'm going to go ahead and multiply just like I would normally if I had 2 times 4 plus 4x, right? I would have to distribute. So I would have 8 plus 8i. Alright, on the bottom here I'm going to do a little bit of side work. And we are going to multiply these just like we had to do in the last slide. We're going to have to FOIL. Okay, make sure everything in this group gets multiplied to everything in the other. So I'm going to get 16 plus 5i. Right, now here's the beauty of this. When I take -5i, I'm going to get, oh sorry, this is 20i. Okay, when I do this, I'm going to get -20i. And this is the nature of these complex conjugates. Okay, and then when I multiply these, I'm going to get -5i times 5i, so it's going to be -25i squared. Red flag on the I squared. These cancel each other out, which is beautiful. That's what we wanted. We wanted the imaginary part to cancel out. And this is going to become a real number because I squared is just -1. So we have 16 minus -25, so in other words 16 plus 25, what we're going to get is 41. So on the bottom we're going to get 41. Now normally what we would go about doing is simplifying these, but these don't really simplify, so we're just going to leave it like this. Here's our real part plus our imaginary part. This is done. You might be wondering, why all of a sudden are we doing complex numbers? Well, this is going to be something where I'm solving for this x. What values of x is going to set this equal to 0? So in other words, we're trying to find what is the solution, or what are the solutions of this quadratic. So the solutions, of course, we could find by, after looking at this, I could try factoring. But there's nothing that I can think of that multiplies to be 2 and adds to be -2. So I'm going to skip the factoring. The other route is we could try to complete the square on this, or we can just use the quadratic formula. Alright, so when we do that, we have 2 plus minus, and then we have 4. This is where we have -8 all over 2. And this is where you might start to see that problem. If you type this into your calculator, you would get an error because you have a negative underneath the radical. So what we are going to have to do is we are going to recognize that there's that negative on the inside, so we're going to have to put an I on the outside. So here I can rewrite this as -1 times 4, and when we break that apart, what we will get is 2 plus minus 2i over 2, And then we are going to break this into 2 over 2 plus minus 2I over 2. Same thing, right? Same thing. Common denominator. You could cram them back together and get this. And then what we have is 1 plus minus I. So here, these are our roots, or our solutions of this quadratic, the x values that would make this function equal 0.
Math joke. Pat.
And there's your homework. Okay.